it's essential that the system works asymmetrically. Because of
I get that. I'm just saying that, from our point of view, we've ended up doing studies that have revealed that the left arm has an advantage for unpredictable mechanical conditions and for unpredictable
I'm sorry, Bob. I don't want to discuss the problem of handedness in terms of time, because it's so remote. Mechanics doesn't give you any clue to how motion is controlled. It's a physics, and from you start from the very beginning. I hope Mark me.
Well, let's kind of maybe let me say a few words to summarize a few things, and maybe not related to control with referent coordinates, but what's been missing so far for me is the word stability, which I think is crucial for what Bob has been telling us. So one arm shows highly stable straight trajectories, but cannot ensure stable steady state at the end. The other arm shows not so stable hand trajectories, but pretty good stability of a steady state. So I've been discussing it with Bob, but I think that the language of uncontrolled manifold here would be very, very useful to make specific models and see whether one arm is, or one hemisphere is specialized for high stability of steady states, and as a consequence, cannot stabilize fast trajectories. And the other one is very good for stabilizing trajectories, but as a consequence cannot stabilize steady states because these things compete. And we've seen, we ran a few studies, and Bob are aware of those studies that suggest that yes, the left arm has better synergies without any movement. These are force production isometric tasks. And the left arm has an advantage in steady state components of such tasks, and the right arm has advantage in preparation to fast action and during fast action. But now, I think, Bob, I think to be fair to our participants who wrote you 16 questions over chat, we should allow you to get through those. If we still have time and energy after you are done with the 16 questions, we may continue. So I shut up, Bob, and please handle the questions.
Bob is still on the first slide. Is he aware of this? Yes. What about ambidextrous people? Do they have similar findings? How are these findings? Okay, in a damaged brain like CP. Neuroplasticity, damaged brain, CP. Okay, I'll answer this quickly. I don't know about ambidextrous people. I've never seen one. I'm skeptical that they actually exist. What I heard is cases in which people have been able to do a highly skilled task with both hands many times in different ways, if you look at them, like the pitcher for the Yankees a few years ago that pitched with his right and left hand and with completely different patterns. I've heard of surgeons doing right and left hand surgery. My question that, being able to switch the instruments from one hand to the other. I don't know if these people are truly ambidextrous. My prediction about ambidextrous would be that it wouldn't be at a high level, because I think that if you will, the number of neurons available, if you're going to have everything represented in each homologous region in each hemisphere, you're going to have less neurons available. But that's maybe just a simplistic way of looking at it. What I've seen is mixed handedness, where people say they're ambidextrous. They can write with one hand, and they can use a fork with the other, and they can throw with the other, and that kind of thing. So I don't know, but there's probably two forms of ambidextrous. One is you're lateralized neurally, and you've learned, like our fencers that I mentioned before, you're able to do really symmetric behaviors because you can recruit both hemispheres for each hand fairly symmetrically. And the other is that you're not symmetric neurally, and so you have less neurons to do everything with, and the result is that you're less dexterous, if you will, and that's the case for many neural disorders. They're less dexterous, and they don't establish consistent handedness. So I don't know if any of that's true. I'm just BSing there, according to what I think. Neuroplasticity, I hate that word because I think that it's minimally relevant to real life, and especially in damage. But nevertheless, it certainly exists. It's certainly there. And I mentioned the idea that it's really hard, or the findings, I should say, that it's really hard to switch handedness. There's not a lot of plasticity in the system. When people do switch, the most pure situation seems to me you lose a dominant hand peripherally and you have to switch. I call it pure because you've got an intact nervous system, and people tested 5-10 years down the road are not commensurate in their skill with, like on average, with people that are age-matched controls using their dominant hand, people who have presumably switched with a non-dominant, and the neural activation profiles are quite different. CP, I don't really know. I guess what you're probably driving at is it possible that somebody could be genetically right-handed? Genetics play a strong role in handedness. Is it possible to be right-handed, but then to have a neonatal stroke and now have your paretic hand be what would have been your dominant hand? I don't really know, and I don't know when. I know that there have been claims that you can predict handedness from in utero behavior, but I imagine there's critical periods for handedness, and I don't really know at what point it becomes very difficult to switch or impossible to totally switch. I hope that answered your questions. Daniela, I was curious to know whether specific brain networks would be more associated to dominant versus non-dominant features of reaching. E.g., stronger involvement of brainstem and frontoparietal networks for the dominant hand, or top-down for dominant control versus bottom-up for non-dominant. Great question. I don't know. I do know that when we've looked at, we've tried to kind of eke out in a really simplistic way the functional neuroanatomy of these systems by looking at stroke patients, and now we're doing brain stimulation work to try and get more specific with it. But what we find is that the left posterior parietal cortex is really important for doing what we're picturing being this predictive thing, at least for learning predictive control over trajectory. And it looks like being able to stabilize at the end point at dorsolateral prefrontal cortex seems to be very important. And if you have that lesion, you have problem on the right side. You have problems with that. So it looks like they do recruit these specializations recruit different brain networks, not that surprisingly. Although we've looked at it very simplistically, not with a network model. How does it work in professional piano players who must be able to control precision? So I think I'm going to go back to, so basically like, what about all those things where people learn to do tasks with their non-dominant hand as good or better or different than their dominant hand? And I think it's very similar to our fencers who became very symmetric just by practicing predominantly, at least with their dominant hand, like intensely. I think it's a matter of hemisphere recruitment. So I think that probably if you look at musicians, you're going to find out that they're using their non-dominant hand for things that we think of as dominant, and they're recruiting their ipsilateral hemisphere a lot more. Maybe not. Maybe they've rewritten things. Maybe their brains look a lot different because of plasticity. Biomechanical University. Is there any parameter that could explain dynamic or impedance as separated function? I don't know what that means. I guess dynamic and impedance, trajectory and position, stabilization of rapid changes, or stabilization of steady state position. I mean, I think all of these are analogs of something that we don't really know what the controller is doing. We can see these things being different, but I'm using language that jives with the way I picture control, which is probably a little bit more similar to the way I sit down and do a simulation on a computer than what our brain really does. But I don't know what you mean with parameter. I mean, when we have these two things separate in our simulations, one parameter is important is how much are you mixing them and how early are you mixing these two modes of control. Sorry that I'm not really answering you. Sorry, I have my mouse is upside down. There we go. Oops. Raquel Gomezin, your opinion. If we train a patient with hemiparesis due to stroke to perform an object manipulation movement with a non-dominant hand, would it be difficult to achieve the same performance of the dominant hand? So I guess this is train patient with hemiparesis. So let's take not a patient and say, if you train something in one hand, whether it's dominant or non-dominant, will it transfer to the other hand? And as everybody here knows, there's been lots and lots of studies, and it seems to depend on what you train. And nobody really knows at this point why things transfer, how much things transfer, or what things transfer, I would say. There's a lot of controversy in this area because there's been so many different paradigms where people have looked at transfer between the hands. One of the kind of cool controversies going on now is that our friend David Ostry from Montreal in Connecticut, in terms of his research, had published some work that suggested that the only aspect of adaptation paradigms that transfers between the hands is explicit components. So when you're fully aware of an error and you're fully aware and you can actually talk about what you're doing, that part transfers. But then when you do the task, you let it creep, the perturbation creep up slowly so people are never aware that they adapt, you don't see transfer. And there's been a number of papers recently that have shown the opposite result. So I'm going to just stay agnostic with this one. I think there is interlimb transfer. We've done a lot of it. We think that what you transfer depends on what you're challenging, whether it's the left or the right hemisphere mechanisms that you're challenging in the task. But so far, there's some evidence for that in our work on visual motor transfer, but there's also contradictory evidence out there. So I have to stay agnostic with that one and say the jury's out. In terms of stroke, whether you can get interlimb transfer in stroke, and you know, I see Monica here. Monica has actually shown some interlimb, right, transfer effects in a number of cases. Actually, the early stuff you were doing, you were interfering with transfer when you did like sequence learning and stuff with particular types of stimulation. I mean, I think there's transfer. I think we don't understand a lot about what is transferred, how much is transferred, under what conditions, and why. And in stroke, it's very difficult because a hemiparetic patient may have damage to different parts of the brain that may be very important in the transfer, so or may not. Please, one question about this is from Fabrice. I'm imagining that Fab's 23 is Fabrice. Who are likely older adults. Did Bob see a reduction of symmetry, as in the fencers, compared to young healthy participants? Fabrice, I'm very upset that you asked this question, and the reason is because, again, I have to answer like the first one. We actually showed, so there's evidence from cognitive tasks. Roberto Cabeza, who does really wonderful cognitive science work, has shown that as that if you take a lateralized function, like for instance, solving a spatial maze task that involves working memory, right? That kind of sequential maze task, that incorporates the right frontal cortex in younger people. In older people, they lose neurons in the right frontal cortex, and what they apparently do is recruit the left frontal cortex, which has similar circuits, a lot more, and they do this for a really long time, and that compensates for the loss of these lateralized circuits, and so they maintain their behavior until they get really old, and then they lose that behavior. So his hypothesis is that you recruit more symmetrically as you get older because you turn those homologous circuits that were doing presumably something a bit different into assisters as you lose neurons in the lateralized circuit, if that makes sense. And we wanted to see if we would get the same thing, so we looked at older adults, and actually what we saw in one of our studies with older adults is more symmetric transfer, and then what we saw in another study in older adults, we did that spring task with both hands, and we saw that older adults actually became more asymmetric in the behavior. So, and other people, it's also a mishmash out there. You get some studies and some contexts that show greater asymmetry, and some cases that show reduced asymmetry depending on the task with aging. So I have to again say, I don't know. The jury's out on that one. Great questions, though. A lot of work needs to be done. Nikita, at what point in human development do you think the predictive and stabilizing control functions begin to develop? Okay, so this is while I don't know, I at least have a better guess here. So handedness is usually assessed by preferences for different unilateral tasks, or preferences for doing a bilateral task, like in the Edinburgh inventory, holding a broom with your dominant or your non-dominant hand down, or you don't have a preference for that. Typically, by 24 months old, children have very consistent handedness. We did a study that we never published because I'm an idiot. I was working with somebody who did parent-child emotional interaction work, and she was using Legos. And so she had all these films, and Legos as a task to work with the parent and child. And I was able to find me and this student, who was an undergraduate student, searched through all this stuff and found these cases where the Legos were symmetrical in front of the 24-month-old, and there was no parental person around, and they were alone with the Legos. And then from those cases, she quantified the degree to which they used one hand to stabilize and one hand to place, to push, to do things that we consider to be more what the dominant hand does. And what she found out is 80% of the 15 or 16 kids always did those consistent functions, always meaning most of the time, were consistent with using their right hand for the pushing and placing stuff and their left hand for stabilizing. And then 2 people were opposite to that, or 20% of the people were opposite to that, 2, 3, or whatever it was. We didn't publish it because at the time I thought we're just looking at things on videotape, and I didn't realize how valid everything we did was, and I feel really bad about that, especially for the undergrad student. So I think by 24 months it's definite, but there have been studies in utero that have shown differential use of the hands for holding and sucking and stuff like that. So I don't know how early. I'm imagining it's a critical period. Okay, Daniela, in your experiments, participants do not typically see their arms, correct? Is there any? So there's a difference when you see your arm. So what's interesting, no vision in the symmetry. With visual feedback, you see a lot more symmetry in reaching movements, typically. And when you take visual feedback away, you see the emergence of greater asymmetry. With visual feedback, you don't get pure symmetry, you get the same kind of trends, but it does reduce the asymmetry. And in the task where you have vision and you've got like tons and tons of targets that I described as being kind of unpredictable, the dominant hand becomes better at that task much quicker within the first few trials. So presumably vision does a lot to help you with making the kind of predictions that we think the dominant hand does. Daniela. Something else that came to my mind is related to an imprecise body scheme for non-dominant hand. Would that make some sense? I guess it depends on what you think of school by Bob Sainburg. Does hemisphere function, lateralization, origins, intrinsic gait, asymmetry? I think this means, does lateralization relate to gait asymmetry? And I wonder, I don't know. I used to talk to Vladimir Zatiorsky about this, and my friend Steve Piazza, both who study posture and to some degree gait. Vladimir didn't do as much gait work, I think. But we talked about posture, Vladimir and I, about the idea of a rambling and trembling trajectory, and maybe the non-dominant system would be kind of a underdamped spring, and the dominant system would be an overdamped weak spring, and you would get differences in rambling and trembling because of that. And I've talked to Steve about the idea that maybe we do tend to rely on one of our legs for more of the propulsive aspect of locomotion and steering, or at least that's what I've heard people in gait analysis suggest. Maybe it corresponds and maybe it doesn't to the arm things. I've seen some studies where people have asked people to do arm things with their feet. So like write their name in the sand and stuff like that, draw pictures. And I just think that's kind of unfair because you're just looking at another effector doing the same function. And so the fact that that corresponds to arm-handedness doesn't really get to the issue of whether leggedness corresponds to arm-handedness. The YouTube channel seems dead. It has changed the link. Got it. It lost the past link. The right and left leg involvement during upright posture. I think this is kind of like what I was just saying. Upright standing. So, I don't know. Like I was thinking along the lines of what information each controller wants. And maybe there's like this differential tuning through gamma motor, gamma statics and dynamics. So the system that wants to predict things about dynamics might want more feedback about velocity, and the other one might want more feedback about stiffness. And if you were to, this is crazy thought, but if you were to in some kind of consistent way modulate your gammas in that way, then your dominant system would be more of a damper, and your non-dominant system, in terms of the reflex responses, and your dominant system more of a spring, underdamped spring. And so the thought there was maybe if you stand in one leg during the other, if you're in your non-dominant system and it's more of a spring and less of a damper, then you would do a lot of trembling and not a lot of rambling. You would stay in place but oscillate a lot. And the other one, where you have a weak spring and more of a damper, you might move around a lot more because the weak spring wouldn't stabilize you in space, and because you have a larger damper, you get less of the high frequency oscillations. That's something I used to talk to Vladimir about, but we never checked it. Okay, do we know what animal species dominance emerged in for the first time? This is a really cool topic. And animals do show dominance. And
well, I understand that you're excited, but also keep in mind that we are kind of 18 minutes past the time. So try to be a bit less excited and more to the point.
Okay, two animals with very clear and well-studied species-specific handedness are parrots and chimpanzees. Other species have individual handedness that apparently hasn't emerged into species-specific handedness because presumably it's functional, but it hasn't emerged as a genetic component of their as a genetic determinant for handedness hasn't emerged among the species. If you want more of the stuff on chimpanzees, Bill Hopkins down in Atlanta has done a lot of work on that, both in the wild and in captivity. In professional ballet dancers, there's always a preferred leg for gesture, and the other is preferred for unipodal standing. Cool. But in the literature, leggedness is not documented. It actually is, but everybody defines it differently. I think, again, intuitively, I think we all have leggedness, or at least most of us, but it hasn't been studied very well. Bob, great talk. I agree. Sorry, I have to run. Sorry. That's from Marco. Footedness is well documented. There are tests of footedness, yeah. Usually people are less asymmetrical in leg action than arm action, but there's dominance. I agree with that. Mark Latash said that. Lewis, Matt, sorry, I realized I made a mistake. I don't think it makes sense. I'm going to stop this, Daniela. Is that okay? I would like to know if it is possible to extend these concepts of lateralization, of reaching to body schema. It's an interesting question. I think we kind of talked a little about that. Thanks, Bob. Okay, bye, Mindy.
Sorry, I have another meeting. I'm going on.
I think we're
Thank
done.
you. I gotta go. Sorry.
All right. Thank you. Sorry for taking so long. I can't hear you, Mark. You're muted.
Yes, now I'm not. The important thing is, of course, is to drink to your health. So thank you very much for the talk, for answering questions, for being patient with everybody, for not cursing.
Great.
Yeah,
that's really great discussion.
That's terrible.
So, cheers to you.
Cheers.
Cheers to both.
Thank you. Thank you, everybody.
Now we can say proper goodbye. Great seeing you all. This Saturday we are going to listen to Monica.
All right. See you on Saturday.
Very good.
Hope we can talk more, Gregor.
Auf Wiedersehen.
Bye-bye.
Bob,
I'm
I'm gonna send to you. Okay.
Bye-bye.
Bye bye.
Bye, Gregor.
Bye, Gregor.
Bye.